So students, we have a guest speaker today. His name is Robert Fragoza. And I'm going to just let him introduce himself and let him start leading a discussion or a presentation.
All right. Hi, everyone. First off, thanks for having me. Second, so this is an AP computer science class. I'm super jealous because when I was in high school, there wasn't an AP computer science class available to me. So you guys are already so ahead of the game. That's really exciting. So personally, I'm a scientist for a startup company in the biotech field called Shape Therapeutics. Again, I work as a scientist. And one of our goals is, without getting too technical, is we're trying to develop new medicines to cure disease. And the specific way we're trying to do it is, I'm sure most of you are well familiar with, there's DNA, about 3 to 4 billion base pairs in each one of your cells. What may be a little less obvious, depending on your background, is that DNA will be first transcribed into RNA. And then from that RNA, that'll turn into all the proteins that you need in order for your cells to actually function the way they need to function. And what frequently happens in disease is maybe oftentimes just 1 or 2 small base pairs within that DNA of those 3-4 billion will change. And suddenly a very critical, unfortunate disease can happen like that. Oftentimes these are called driving mutations if, for instance, you're researching cancer. Now, one of the hardest challenges is going through all of that DNA available and trying to pinpoint which mutation is responsible for disease. And then even tougher than that is, once you've found that mutation, how do you actually do something about it? And so where our company is a little bit unique, and why I'm so excited to speak with you guys today, is we are trying to take computational approaches as well as laboratory approaches to, one, of course, identify these mutations, but then using, it turns out, proteins that are already available in your cells, we can actually make precision edits within that RNA. So that was the guy in between DNA and protein. Make small changes to it that will correct what went wrong that caused the disease, and then turn it back into its original function. And in that manner, hopefully you can bypass the disease. That bad protein that came from the bad DNA, from the bad RNA, we put in that precision edit, and then suddenly, hopefully, we lead to a therapeutic cure for that. And I will get into that a little bit more today, but I figured I'm hoping what might be a little bit more useful for you guys is to actually get a little bit more into my background. And what I hope is, maybe there's a few of you guys out here that are more interested in a biological side of it. And so hopefully learning about how I got into this, because there is no direct route, unfortunately, can help you guys get a better appreciation for all the really cool things you can do with a computer science background. It is just tremendous, the opportunities available. So I was an engineering major in college. Actually, I was a chemical engineering major. But fortunately, because I was in engineering, that's when I was first exposed to computer science. We were all required to take a course in C++. I imagine you guys do Java or maybe Python. Java is exciting. But I first learned C++, and I got to confess, maybe you guys are way faster than me. But my first semester of C++, I thought it was one of the hardest things in the world. It wasn't intuitive to me at all. But I stuck with it. And eventually, in engineering, oftentimes you can get involved in research with your professors. And that was something that really, oh, if at any point you guys want to interrupt with questions, by all means, don't. This is meant to be discussion. You guys can always do that. But I got involved in research, and part of the research I was doing is biological in nature, but we started going through this type of DNA sequencing data. And when you have 3 to 4 billion different base pairs, so those A, C, G, T's, G, T's, there's just no way you're going to look through that manually. You can't annotate that. You can't figure it out on your own. So where computer science really started to take off for me is the only way to look at that sequencing data perfectly and look at all that DNA that's encoded within your cells is to actually take these computer science approaches to handle all of that big data. And I'm sure big data is probably a term you guys have heard tossed left and right. And the reality is, in biology, it dominates everything we're doing. We're really good, it turns out, at sequencing human genomes. What we're less good at, and if you ask me frankly, I think what we're pretty lousy at, is interpreting what each one of those differences does. So when I got involved in my own research, it was trying to figure out, using not actually just computer science, but something we call bioinformatics. It's a combination of statistical techniques as well as computer science to try to piece together what it really is, what patterns you're looking for in order to interpret which mutations that you might, those changes in DNA that you find in your genomes that might actually lead to something. So specifically, the research I was involved in was we were studying, maybe some of you guys are familiar, we were studying autism. And what's so fascinating about, now autism, fortunately, I've been very lucky and it hasn't affected anyone in my family, but I imagine you don't have to reach too far to find someone who has been affected by it. And in autism, what's fascinating is, many of you guys will know, your DNA is inherited. You get a mix of what your father has and what your mother has. And so most of those DNA, your DNA is 99.9% the same as your neighbor, as anyone else. But within your family, it's almost close to 100%. But what's so interesting about autism is that when you're born, it turns out you get about somewhere around 20 to 40,000 different mutations. And 20 to 40,000 may sound big, but I want to remind you guys, you have 3 to 4 billion base pairs, different individual pieces of DNA in your cells. So 30 to 40,000 is small relative to that. But it turns out, depending on those mutations, they're going to occur in random spots. And it turns out, you can just get really unlucky and it hits a certain gene or a certain set of genes, you get a mutation, and it winds up leading to an autism or a developmental phenotype. Sorry, that's a little too technical. It can lead to a condition like autism where you didn't get it from your parents. Oftentimes the parents are just fine. It just happened that that individual got very, I hate to say, unlucky. They didn't do anything. You were just born with it. And so our research was, this is where it's really, really cool, right? How do you find a new mutation? So the way you do it is, if you suspect that you're trying, you'll see it behaviorally that there's along the development of the child, something is just a little bit wrong. And that will turn out happening. Parents are watching their kids all the time. They'll see it by around age 2 or 3, and then certain tests will be done. Physiological, the doctor, diagnostician will observe the child and they'll start checking off things. And that's often how autism is diagnosed. But if you want to find the mutations, right, the genetic components, and there are genetic components that contribute to autism, not genetic alone, but they are major factors in it. How do you actually do that? And so what's fascinating is what you need to first do is you'll sequence the father and you'll sequence the mother. And you have to sequence each one of these 3-4 billion base pairs. And then what you do, and that's a lot of data to keep track of. So wonderful to have a computer science background. It's like, import this, you're gonna hash, these are the mutations, we'll hash those mutations here. Here's our reference, we align the sequence, all technical terms, doesn't matter. You guys are more than capable of it given enough time. So what's fascinating is once you sequence both of them, then you sequence the child that's affected. And what you do is, and maybe some of you guys can already answer this, is you're going to look for all the individual differences in the child that the parents don't have. And if you can do even better, oftentimes the autistic individual will have a sibling, an older sibling perhaps, that is also unaffected. And the more people in that family you can sequence, and unfortunately, generally, there might only be 1 or 2 children, so you don't have that many options, the more mutations you can rule out and go, these are the set that are completely unique to this individual. And so that seems pretty straightforward, right? But I just told you guys, you have maybe, it can have up to 2,000, 20,000 different mutations. How do you pinpoint the ones that are actually leading to autism, right? Most of them probably don't do anything. And so that's where our research came in. The sequencing, we know how to do that. Again, one of the things I said early on is the coding part of it isn't really the biggest challenge. It's how do you actually infer which mutation is having that effect. And so what's going on is there's a lot of research grants, a lot of active research, and a lot of biotech companies trying to look into this. And what's happened is a lot of individuals are impacted by autism. So what we've done is we've sequenced individuals from over 2,500 families where the child is afflicted with autism. And what you do in those cases is you keep doing this. We call them trio studies. So there's 3 of them, the 2 unaffected parents and the affected child. And if you can, an unaffected sibling. And what happens is, even though you won't see the same mutation every time, because again, there's so many of these de novo ones. We call them de novo. That's just a fancy term for not from mom or dad. It's just completely new in the individual. You guys have de novo mutations. All of you do. It just didn't happen to hit you anywhere where it could lead to a developmental disorder. And so, but what happens is, and maybe you guys know something about this, but I'm glad to give details. Even though you have 3 to 4 billion base pairs, you only have about 20,000 genes. And the genes are those sets of DNA pairs that will lead to the proteins that encode into your body. You guys may even know some of them. One of the most famous ones is called TP53. It's heavily involved in cancer. So the human genes are what wind up encoding for proteins. And it turns out when you sequence that many families, even though the mutations are different, they start hitting the same set of genes. And this is a beautiful thing to observe, because once you know the set of genes that are responsible, and hence that set of proteins that lead to autism phenotypes, then this is where medicines, and we're really early in this. I don't want to oversell where we are. We're just getting into the biology. First, we need to understand the disease before we can pursue therapeutics. But once you know who the proteins are, that's when you can start developing medicines in order to actually go after and hopefully combat what is otherwise a very debilitating disease. So I see I've already been talking for a little while, but I apologize, but I hope you've been getting something out of it. I do want to cover one more thing. Sorry, Alexa, if this is a little bit loose. I just didn't know it was going to go there. Alexa, I hope a lot of you guys are going to pursue engineering degrees or computer science degrees, or it's all something in STEM. That's my passion. But STEM is, I'm also, I can't. I always want to be very honest. STEM is hard. Let's just be completely honest about it. It is really hard, and I can't speak for the experience of others, but for me, it was difficult. And along the way, I came from a small school in Southern Arizona, and I was always used to, you guys are AP computer science students. I bet you guys are, you're the smart bunch within your school. When you pursue an engineering major or anything in STEM, everybody is smart. Everyone is smart. And because I love statistics so much, that means a good fraction of you will become average within that pool. Don't take that too literally. It's just, if you get enough persons, what is the mean? It's going to be right there near the median usually. So it can be, for me, it was very challenging because you're used to performing at a certain level. And suddenly you get to college and it's like, whoa, man, there's a lot of B's showing up on my transcript. What's going on here? Like that's new. And I remember, you struggle through exams, and it is weird. I remember because I was a chemical engineering student, going into my first chem final, and at the end of the final, I heard a student crying. That's just like, oh wow, like it really beat someone up like that. And I had a lot of moments where you suddenly start to think like, am I really good enough to do this? I'm not performing the way I wanted to. Internships were going to other students. There was always someone doing better than me. And, I come from a Latino background, and suddenly a lot of your colleagues are white and Asian. That doesn't mean anything, but you notice, I grew up in Southern Arizona, and it's just like, oh, the people don't look as much like me. And you start to feel a little bit like an outsider. And if you start to struggle a little bit, you can almost start to think like you don't fit in. That happened to me. And I can only speak for myself, but it's also it wasn't the right mindset. For me, it was, again, you find these excuses where, oh, maybe I'm just not good enough. For whatever reason, I wasn't trained well enough. I didn't go to the best high school. I didn't, my parents never went to college. My parents never even graduated high school. Maybe I'm not cut out for this. I wish I knew a secret way to do this, but somehow along the way, you got to learn how to take all that weight, at least for me. And maybe it's the same for you guys. I hope not. And you got to learn somehow just to put it over here for now. You know what? I have my worries. They're never going to fully go away, but I'm just going to put it over here, put my head down, and just keep working my butt off at it. and you have a lot of late nights in the library. I don't know a better way to do it. Or you just sit in front trying to get that piece of code to work, trying to figure out what the answer to that differential equation is. Why didn't my MATLAB program compile properly? And you just do it. And I set a goal for myself. I was an honors student when I was in high school. I'm going to be an honors student when I graduate college. I made that happen, and it wasn't easy. And I wish there was a recipe that I could tell you, do A, B, and C, and that'll happen for you too. I don't think that exists, because you're all different. You all have your individual talents. The only real takeaway I can give you guys is, if for some of you, and it will probably happen. I hope it doesn't, but a large enough group, you're just as talented as when you started. It's just, some people just had better training. It's a reality. But if you really work your butt off, you can catch up to anyone else. You really can. And I know you guys are already smart if you're taking AP comp sci. You're good enough. The reality is you just got to start working hard enough. And it does get harder because, again, the reality is when you go into these engineering majors, everyone was just as smart as you. So, the work ethic is what I think personally takes you over the top. And all those little feelings that you might get, you learn to push it aside. And once you're improving yourself, you just start feeling better over time, and that can lead to great opportunities. So just, for those of you, if it does happen, just keep your confidence up, keep working your butt off, and I know you'll get there. It does work in the end. Sorry, I probably spoke way too long. But maybe I can open it up to you guys. I went way off topic. I apologize. I hope the autism discussion was a lot of fun.
Still forming my question. It's what was I trying to ask? I guess I'm interested in when you were researching autism or other subjects as well, if you'd like to speak about something else. Um, is it mainly research focused, I guess science focused, or is it more data focused or data analysis?
Okay, so that's a fantastic question. So William, I hate to nitpick a little bit. So I think both of what you said, research or data analysis or data, informatics, digging through stuff, I think they're one and the same. So I'll tell you about something I was just working on right now for my company. I don't know if I'm allowed to say it, but whatever. So oftentimes, we have a platform right here where we're able to make these specific changes in the RNA that I was talking about. And we have a very special way of doing it so there's 4 base pairs, A, T, C, G, and DNA. And then it's A, U, G, C, and RNA, and technical details. But because you have this platform, what you can do is, you look at, okay, where do I see a U, and where do I see it in this specific oligonucleotide context? I apologize, just a certain stretch of text, call it 20 letters. And do I see that same 20-letter set of text anywhere else? Well, now that's informatics. So it turns out there are a lot of databases publicly available online. And I wound up building a little tool. Maybe you guys figure these kind of things out soon enough. It's a tool called Beautiful Soup. And what it does is it parses HTML text. And then you combine it with another tool. So basically what happened here is I went into public little databases and wrote a little tool so that my server would automatically ping it every 3 seconds, take the query that I want, parse the HTML to search for those 20 base pair patterns that I was looking for, so I could find a list of diseases where I could apply this everywhere. It's a research question, but oftentimes you have that research question in mind, and now you need to find all the other information that supports what you're trying to do. So I had one question in mind, and I knew where I could get it, but I knew I wasn't just gonna, oh, let me look at this page, write this down. That's not gonna happen. Oh, let me look up this website, that's too slow, right? So it's like, oh, hey, well, let me just parse it online. I'll build it'll ping it every 3 seconds. It'll put it into, it'll put it into a little text file. I'll spit that out at the end and then parse what I want. I apologize if that sounds way more technical. I imagine there's some of you where that just sounds trivial. And given enough time, it'll be trivial. So I think they're the same thing. So for me, you start with the research question, and then you follow it up with all the databasing that I need in order to get all the information to answer that question. I'm sorry if that was a little loose. Is there something more specific you're after, William?
No, that makes sense. Basically, the data analysis is a good way to, focus your research more and I guess narrow things down a lot. I guess I have a follow-up question. I'm not sure if you know much about AI, but I'm also
Oh,
curious if you don't know anything about AI, how do you think this would change the researching process or anything along those
so
lines?
yeah, so I'll tell you what I know. So you're saying AI. I like to call it machine learning. It's more or less the same thing. And I'm sure that's a term you've probably heard. So what we're doing is we're designing, we'll keep this between you and I, William. So oftentimes what we do is, so here's, right here's my mutation of interest. And I want to design another piece of RNA that comes in and binds it and binds its stretch of DNA. And I'm trying to learn that, then this next protein comes in and goes in and changes it to the letter I want. The problem is this protein, he's rather promiscuous. He'll go over here and do something, and he'll go over here and do something. And I don't want him to do that. I want you, because in disease, I want to fix that one mutation, and I don't want you to change anything else because you might just make things worse. But it's looking at a stretch of letters, and I'm never going to find a pattern there, not by eye, at least not me. However, if you feed a machine learning algorithm enough data, and we can, specifics will have to be for another day, I apologize. But through machine learning algorithms, if I just keep feeding it, okay, here's my sequence here, here's the sequence here, and here's the result for it, here's the sequence here, this is what it did, here's the sequence here, you get the point. Through this black box, and be more specific, we'll use neural networks another day. Unfortunately, there's no time to describe these things. You will start dissecting the patterns. And suddenly, what I couldn't see, the machine will tell me, well, 80% of the time there's an A right here. And if you couple that with the C over here, and then it bulges like this, that's when we see the most specific level of changes where you want it to be. And that's just something because there's so much data, I'm never going to see it on my own. So that's where machine learning really becomes a big deal for us, because then we can actually, computationally, your network can see what you just won't. But if you learn the statistics behind that network, you can interpret what the algorithm is spitting out. And then suddenly we have this, oh, here's the design now. Let's try this. Oh, hey, our specificity went way up. And maybe now we can cure what we're after. And this, I'm describing to you in 5 minutes what can take months, if not years. But I hope that got a little bit closer. I know I wish we should have a lesson on this. I'm sorry, but in machine learning is the answer. You said AI, I say machine learning, but I think it's just two sides of the same coin. Does that help a little bit, William? Sorry.
Yeah, actually, I think that answers most of my questions.
No, it's a good question. I wish we could get into specifics because this is where research just gets so much fun, because you spend the day just thinking about this and getting it to work. And it's really a joy when you go home and you're just so excited to come in the next day because, oh, I know I can get that. And it just takes time.
I could hear a bit more about your workday.
Absolutely. So that changes quite a bit. So, first I was a graduate student. And as a graduate student, my workday started whenever I could wake up, because no one actually picks your hours for you. So as a graduate student, sometimes I'd be in the lab till like 10, 11 p.m. That's not required, but I was just kind of a night owl, and I'd get so excited by what I was working on. It was just easier for me to stay late. And then you'd have to drag yourself up at 9 a.m. sometimes, because that's when your lab meetings would start. And so the way that would work is you'd come into your lab, you have your desk space when you want to do your programming, but then I was also on a lab bench doing, running my pipettes, putting in your reagents, doing the experiments that you need to do, handling your cells. You go lab meeting, and that's a whole bunch of fun, because the type of discussions we're having, you're in a room with 10, 20 other people, and then you're actually getting into the details of it, right? Here, I just described machine learning. Well, how do you run that algorithm? What's your code look like? You can actually start dissecting that. That's a lot of fun. You get into a little bit of debates with other people. And so, I think your code is wrong. This is wrong. That experiment's not, that's just data. It's not going to show us anything. Oftentimes it's a little bit of competition, because you'll have individuals who are specialized in, taking care of the cells and running the experiments that your data says, oh, okay, here's the sequence we want to try. You run that experiment. So that didn't work. You don't know what you're talking about. It's playful, trust me. But you get better. The machine learning is a black box, but it gets better with you. You're never absent from the equation. So, one of the realities is, though, at least for graduate school, and I talked about the job as well, on average, it takes in biomedical sciences, and I shouldn't tell you this, guys, because you'll get intimidated, and you shouldn't. It could take 5 or 6 years on top of the 4 years of college, and that is intimidating. When I was first an undergrad, I was already pumped. I was like, oh, college is another 4 years. I mean, I want to do it, but 4 years is a long time. And it's like, oh, you're going for a PhD. Why would you want to spend another 5 years? That's ridiculous. But as I got involved in research, and I didn't think about it as those 5 years that were going to come up. I thought about it as the career that I was going to get as a result of it. Like, it isn't school anymore. You're in a laboratory doing research. In grad school, I shouldn't speak so loosely, but your academics just don't matter as much. They matter to get to grad school. That's an unfortunate reality. But once you're there, what matters is publishing papers, and you get into a competitive environment, a healthy type of competition. Sometimes, the way maybe athletes do. You're playing basketball with someone, you start going to court later because you want to beat them the next day. But in a friendly way. No one's trying to gun you down, nothing like that. It's just like, oh, I know I can do it better. And for me, that's fun. So your hours get long, but it's not because someone's telling you, oh, Robert, you need to be here 10 hours today. It's never that. It's that, oh, I think I'm close to something. And so you go after it. Now, as you grow older, eventually you'll want to start a family, something like that. Your hours will have to control themselves. And again, it's not nobody's telling you, oh, be here 9 to 5. It's just you start to have other obligations, and you have to get better with your time in order to fit them in. So, my days end now that I'm at work. I've started my career. My days end a lot earlier. I apologize if any of that sounded intimidating, because the reality is, once you're really excited by something, and this is, if I can give one lesson, and it takes time, it's different for all of us, but if you can find that thing that just excites you so much, it's never work. It really isn't. I mean, sometimes it's work. I got to meet with my boss today. That's never as fun. Let's be a little bit honest. Sometimes it is work.
To end, I have to let the students.
Oh yeah, sorry. I see. Sorry guys, I told you I could go down rabbit holes. Sorry.
That was a wonderful talk, though. I liked all the rabbit holes you went down. Thank you for being with the students. Students, if you want to give them a virtual round of applause, that would be wonderful. And thank you so much, Robert, for being with me.
No, thank you guys. Thank you for having me. I apologize if I went down my rabbit holes, but if you guys ever have any questions, go through a lesson. I'm sure you can find a way to reach out to me. I'd love to hear more from you guys. If any, I'll let you guys go. You guys have a good one.